To introduce our next speaker of the day, we humbly request Mr. R.S. Kumar, Chapter Treasurer, to introduce Mr. Vinayak Ghotge, Vice President Business Development, Forace Polymers, to our esteemed audience.
I'm happy to introduce Mr. Vinayak. He is a BE Metallurgy from College of Engineering, Pune in the year 1985. He has more than 36 years of experience. He worked in ferrous and non-ferrous foundries, and then he joined the chemicals manufacturing companies like Fasico India, ASK, Gargi, and he is having more than 35 years in product management and sales and marketing management in senior position. Presently, he is working with Forace Polymers Private Limited, Haridwar, as Vice President Business Development. He is looking after refractory coating and technology. Mr. Vinayak has presented technical papers on refractory coatings and sand additives at various forums in India and abroad. I welcome Mr. Vinayak. The stage is for you. Thank you.
Very good afternoon to all of you. At the onset, let me thank IIF Chennai chapter and organizing team NFD Celebrations for giving me this opportunity to present my thoughts before you. Let us first talk on the technological developments which have happened over last probably 2 to 3 decades. About 30 years back, most of the automotive foundries, they were using shell as the core making media, and then there is a changeover from shell to cold box. And now in the recent decade, you must have seen a lot of core centers into the place. And because of the change in the core practices in the automation also, there have been changes in the coating practices as well. The coating of core assembly as a package, either by dipping or by overpour process, and use of single coating. In the past, the preferential coating practices was possible. For example, doing double or triple coating only to water jacket core or the port area or the blow-by core. It was possible to have the selective coating practices, and then they used to assemble the cores. Whereas now, once you go for the assembly dipping, then the use of single coating became the need of the hour. Definitely, the change in the technological development have led to a lot of advantages, as high productivity, less handling of the system, cost optimization, and of course reduced rejection. High strength, low consumption cold box is one which is now is being used by most of the high productive foundries. Advantages: high out of box strength, low consumption of the binder, cost effective, and also because of the low consumption, the gas related defects are low. These are some case studies where we have been able to establish low consumption cold box, and here the binder was initially used at 0.9 and 0.8 addition level. There was offset addition, and we took trial at 0.7, 0.7, and the castings were, the cores were also quite good. The scratch hardness was around 65 to 68, and the casting finish was also quite good, and now they have been using this binder on a regular basis. In the second case study also, earlier they were using at about 0.9, which is now reduced to 0.75. In the case 3, it was being used at 0.85 earlier, and we will be able to reduce it at 0.7. I'm not going into more details in this because most of these additions and everything you are quite familiar with. I'll go into details in the other slides also. But having chosen the high productive binder system, then there are some limitations or the disadvantages which are always associated with cold box system. Is cold box, as you know, it has relatively low strength compared to shell or other binder system. So naturally it has a problem of getting veining defect. Then there are other problems which are faced by the foundryman, like sand sticking, sand fusion, and internal passages unclean. The cleanliness of internal passages has become the demand now because of the restrictions or because of the higher stringent demand put by all the OEMs. If we go through the casting buyer needs, not only the internal casting finish, which is a design requirement in terms of the engine efficiency, even the external casting finish also they need of a higher degree because of the aesthetic look. Then of course defect-free castings, and major defects what foundries encounter is scab, veining and inclusion. Then close dimensional tolerances, good machinability of course, and reduced casting weight. As you know, if you think about the cylinder head over last probably 12 to 15 years, there could be a reduction in the casting weight to the tune of 30 to 35%. And because of on one side there is a reduction in the casting weight, on the other side there is improvement in the output of the engine, which is also to the tune of 25 to 30%. So surface defects, if we compare, external surface defects are possible to eliminate during fettling using modern tools and techniques. But internal defects, it is difficult and time consuming, and at times it is costly also because it directly affects the engine efficiency. This is the veining defect. As you know, silica sand has the ability to expand 2% by volume at a temperature about 575 to 580 degrees centigrade, and then the sand also it converts from alpha phase to beta phase, and then there is a cooling also. Because of the heating and cooling cycle, there are stresses developed in the core like this. And when the stresses are developed in the core, those stresses lead to cracking of the core. This is how the veining occurs into the casting. So as I have told you in the beginning, the factors affect veining is the low strength of cold box. If you compare different binder systems in terms of strength and its susceptibility towards veining, as you see, the cold box is at the bottom. So how to control veining is you can use different types of sands which have low thermal expansion, say like zircon sand, chromite sand, carphalite or ceramic sand. Use binder with adequate hot strength and use anti-veining compounds or anti-veining additives. The anti-veining additives are of different types: organic, inorganic and engineered sand additives. This is the broad comparison between organic and inorganic additives. Organic additives like say wood flour, fiber granulate, starch, dextrine or carbonaceous products. They are reliable in handling, good anti-veining properties, but the main problem with this is high gases involved. Although the addition rates are quite controlled between 0.5 to 2%, they evolve a lot of gases, and hence it is difficult to use organic anti-veining compounds in the critical core areas where the core volumes or the core shape is, the core thicknesses are quite low. Against this, inorganic additives like say red oxide, black iron oxide or the ceramic or the glass, they evolve very low gas, excellent anti-veining properties. The difference, one more difference between the organic and inorganic is, in organic additives, they burn and they have a gaseous, they are converted into gas, and this is how the voids are created between the sand, around the sand particles, which take care of the expansion of the sand. In case of inorganic additives, normally they don't burn. From the solid state they get converted into plastic stage, and because they are into plastic stage, they are able to accommodate the sand expansion. This is the main difference between organic and inorganic. The disadvantage is, of course, high addition level, because you need to add the quantity adequate enough to coat each and every sand grain, so that when the sand grains attains a temperature of around 600 degrees centigrade, then the material, the coating has to get converted into from powder stage to plastic stage, so that it is able to accommodate the sand expansion. See, the addition rate is normally high, and at times, yes, it also have the problem of vent blockages and other things. Then comes as engineered sand additives. It's a combination of multiple components, multiple materials used in the practices, and they typically provide some fluxing action that change the expansion profile of the silica sand. And we have different types of anti-veining additives which are used. They are both organic as well as inorganic, and the addition of organic varies between, say, 0.5 to 2%, and inorganic anywhere between 3 to 5 to 7%, depending upon the criticality of the veining defect. I'll just go through quickly the certain field trials we had taken in some foundries. This was a foundry where they were earlier facing a problem of veining as well as sand fusion in the cylindrate area. They were using this with fresh silica 80% and 20% reclaimed sand, and this was taken trial with only 100% silica sand with anti-veining compound about 4%, and if you see, the veining was also eliminated, and even the sand fusion, there was no sand fusion into it. Similarly, especially the internal passages, like say water jacket area or the oil passages core, where foundries often face the problem of blockages. So normally chromite is very commonly used. Zircon sand is one which is the best, but then the price is the prohibitive factor. Chromite sand is widely used, but then in automotive foundries most of the core making is done through core shooters. So if you use chromite sand is very angular, so naturally it leads to wear and tear of core boxes much faster compared to just silica sand. And third is the ceramic sand. Ceramic sand is again an engineered sand which is absolutely spherical in nature. If you see the use of ceramic sand definitely is much more advantageous to automotive foundries compared to chromite sand. It also helps in better compaction of the core. These are some field trials we had taken with the ceramic sand, and earlier this water jacket core for the block was made with the chromite sand, almost 40% of chromite sand, and despite using so much of chromite, still they were getting sand fusion defect. This is a boroscope photograph which is attached. This core was made with 25% ceramic sand, and absolutely no sand fusion obtained. Clean water jacket passage. The advantages foundries get with ceramic sand is excellent flowability of the mixed sand, very good compaction, dense core, better smooth surface finish of the core compared with chromite sand, and reduced addition from 40% chromite, they could come down to 25% of ceramic sand. So there was a cost saving also involved, and the rejection was also controlled from almost 40% to 9%. Then comes new generation coating. Okay, most of the foundries use refractory coating, and earlier almost one type of coating was used for most of the cores. But now, because of the stringent requirement of the OEMs and also requirement with respect to the high power output of the engines, it is required that we should give preferential treatment to critical castings, especially water jacketed blocks, heads, etc. The new generation coating is basically carefully chosen refractory combination by understanding the need of the casting. It has high resistance to metal penetration at casting temperatures, and the optimum rheological properties also give consistent coating thickness for even your assembly dipping as well. And good bond and wetting properties are common, it's required anyway. This is a cylinder head casting at one of the foundries where they were having a problem of severe veining in the port core area, and there was also blockages of passages internally. So trial was taken here with the combination of anti-veining compound as well as new generation coating. So they were having a problem of, even though they were using 100% thermally reclaimed sand, still they were getting the veining. So there we used a anti-veining compound, and then after making cores with use of anti-veining compound, then we used the complete package into the new generation coating 144 plus, and this is how the casting feedback. The cut section, you can see the cleanliness, no veining, no sand fusion. So the benefits Foundrymen got is sand fusion blockages were eliminated, veining eliminated, excellent surface finish of internal passages, reduced fettling of course, and the faster movement of the casting. Overall, of course, there was overall cost reduction as well. So use of thermal expansion, low thermal expansion sand, additives, anti-veining compounds and advanced coating help Foundrymen to produce castings with reduced defects, improved surface finish, excellent internal cleanliness, and most of the times the end-to-end costs are taken into account. It also works out to be economic. Thank you.
Thank you, Vinayak sir, for throwing light on different processes, coatings and additives which help in achieving higher productivity, which is much needed for foundries. Thank you so much. Do we have any questions for Mr. Vinayak, please?
A good presentation, sir. So I have a doubt in 4-coat 1/4 plus. What is the base element for that, sir? And what is the percentage we should use as a combination with regular anti-veining agents?
No, 144 plus is a coating.
Yeah.
So it's a mixed refractory coating, basically graphite, but mixed refractory coating. And coating is, see, normally for any critical cores, like say water jacketed blocks or heads, of course, what you need is a highly insulating coating. Okay, the coating should have very good insulating properties. At the same time, now a lot of coating suppliers or the foundry chemical supplier, they said that we have an anti-veining coating. I mean, normally if only coating can eliminate the veining, then I don't think, I personally don't believe that, mainly because the root cause is not coating, the veining root cause is sand. So basically if you work on sand, then there is no need. But at the same time, having worked on sand, but still you tend to come across veining, because like I have one case study I have shown where despite using 100% reclaimed sand, still they were getting veining. Now, coating helps you to arrest veining to some extent. Okay, that is one. So 144 plus is a coating which can be used to arrest veining to some extent. That is one. And talking about you also wanted to know about the anti-veining products, correct?
Yes.
Anti-veining compound you can use if you are using organic compound. If you have a bulky core, chunky core, where you are able to vent out the gas easily, you can go for organic anti-veining compound. Those work out to be economical also, and it work out to be effective also. But if you have very thin walled cores and where removal of gas is really an issue, then you should go for inorganic anti-veining, and the addition rate varies between 3 to 6% depending upon the criticality. Hope I have answered your question.
Yeah. We have used AF2 mg and also AF6 to the percentage extent of 4%.
Yeah.
So still we have the issue of weaning.
We have to see. That is why the addition rate cannot be standardized. It depends upon the criticality of the casting, where it is coming. So based on that, you need to optimize the addition rate. That is the reason normally if you see inorganic addition rate, people say between 3 to 7%.
Even 7% can do that.
Yeah, you can go higher addition also. That is not an issue. It will only at times it will add to your cost. I mean, but then again I have seen the cost has to be seen end to end, not a product as an individual.
Okay, sir. Thank you very much.
Thank you.
Any further questions, gentlemen?
Yeah.
One is my mixing, 100% I am not getting that veining. Some 5% only we are getting the veinings. That is the one question. So another one, if I am getting that veining, so three options is there. One is the anti-veining additives we can go. So chromite as you told. The another one is the coating. So which one I need to prepare?
It depends. If your veining is very minor, see veining, if you have less than 1 mm, just a line of metal penetration, thin line of metal penetration, probably coating will do the job for you. It depends upon how badly the core is getting heated while casting is being solidified. See, it all depends upon that. If your veining is very, very severe, sometimes the crack is so much that the veining is almost about 5 to 6 mm inside, and then such metal penetration is difficult to clear also. So it depends on your casting and on your process. So if you are able to do it with coating, no problem. But the coating, in my opinion, as a metallurgist, let me tell you, coating is just a supportive thing. If you have to really work on the sand to eliminate veining. That, as an engineer, I will tell you that.
Or any development.
You have to use thermally stable sand.
Okay.
Thank you, gentlemen. To now felicitate our speaker, Mr. Vinayak, we now request Mr. Rajmohan Madhyaragan, Joint Secretary, IIF Chennai Chapter, to felicitate the speaker with a traditional Angavastram.
Thank you so much.
To now felicitate our speaker with a memento, we now request Mr. R. Palani Murugan, Honorary Secretary, IIF Southern Region, to felicitate the speaker. Thank you, gentlemen.